So welcome dear learners in maintenance and testing of electrical machine, week number 4, lecture number 1. And today we will discuss about the EMF equation and torque equation for DC machine. The basic objective of this is lecture to understand and derive the EMF equation for DC machine. Also we will see how we can what are the different significance of back EMF in DC motors. Also we will discuss about the torque equation, and we will see how we can solve the numerical problems which is associated with torque equation and EMF equation of DC machine. So let us start with this EMF equation, how we can derive the EMF equation for DC machine. Basically this EMF is known as electromotive force for DC generator, which can be derived using the Faraday's law of electromagnetic induction, which states that induced EMF in a coil is equal to the rate of change of magnetic flux through the coil. Now we can see how we can derive those EMF equation. So the first steps in the derivation of EMF equation is the assumptions and definitions. See, the capital P indicates the total number of poles in the machine, whereas the phi indicates the magnetic flux per pole in Weber. And the next assumption is N. Capital N is a speed of the generator in revolution per minute, more commonly known as RPM. Capital Z is the total number of armature conductor present in the armature windings. And capital A is the number of parallel paths in armature winding. And as we know, for wave winding, this capital A, that means the number of parallel path is equal to 2, and for lap winding it is equal to number of pole. Now we will see how we can derive the EMF equation, which is start from the flux cut by one conductor in one revolution. See, each conductor cuts 5 flux from P poles in one revolution. Therefore, total flux cut by one conductor in one revolution is P into phi Weber. Okay, and revolutions per second. So the generator speed is N, which is given in RPM. Okay, so convert it into revolution per second, which means N by 60 revolutions per second. Okay, so flux cut by one conductor in 1 second, how we can derive this? So it is very simple. Once in 1 second, the flux cut by one conductor is equal to P into phi into N by 60, which is the flux cut in per second. Okay. Now we will see the EMF induced in one conductor. According to the Faraday's law, the EMF induced in conductor is rate of change of flux linkages. It is very important what we call the point. So therefore, the EMF induced in one conductor is E is equal to P phi N upon 60, whereas E is the induced EMF in one conductor. So as you know, it is a EMF for one conductor. Let us understand the total EMF induced in the armature. The total number of armature conductor is Z. Okay, so those conductors are divided into A parallel paths. Hence, number of conductors in series per parallel path is Z by A. Therefore, the total EMF induced in armature is given by multiplying the EMF per conductor by the number of conductor in series. It means capital E, which is the induced EMF in the armature, is equal to E into Z by A, whereas small e represents the induced EMF in one conductor. Okay, so by substituting the value of E, you will get the induced EMF in the armature, which is E is equal to P phi N Z upon 60A. So therefore, the final EMF equation we will derive as a capital E is equal to P phi N Z upon 60A. See, this is the EMF equation for this generator, and this EMF is known as the back EMF in case of DC motor. So let us understand what is the significance of this back EMF in case of DC motor. So back EMF is known as a counter EMF in case of a DC motor, and which plays a crucial role in operation of DC motor. Okay, so it is the voltage generated by motor itself when it is running, acting in opposition to the applied voltage. So it is definitely opposing the applied voltage in the case of DC motor. So there is some important points which is associated with the back EMF in DC motor. The first point is the regulation of motor speed. So self-regulation mechanism. The back EMF helps in regulating the speed of motor. When the motor speeds up, the back EMF increases, therefore reducing the net voltage across the armature and thereby limiting the current which is flowing through the armature. This helps in preventing the motor from running too fast. Okay, so therefore it is acting as a self-regulating mechanism in case of motor. The second point is the speed control. The motor's speed can be controlled by varying the applied voltage. Okay, so as the speed changes, the back EMF adjusted accordingly to ensure the stable operation. The next point, the next significant point of back EMF in DC motor is the protection of motor. Okay, so current limiting. As a startup, the motor armature is stationary and there is no back EMF. Only resistance to current flow is the armature resistance, which is usually very low. This can result in a high inrush current. As a result, motor picks up the speed, the back EMF develops and limits the current to a safe limit. The next one is the overload protection. If the motor is overloaded and slows down, the back EMF decreases, leading to an increase in the armature current. This can trigger protective devices to shut down the motor and prevent the damage. Energy efficiency. Energy conversion. Back EMF represents the conversion of electrical energy into mechanical energy. It is a sign of that motor is performing work and converting energy efficiently. The second point is the power consumption. The presence of back EMF reduces the effective voltage across the armature, thereby reducing the power consumption and the motor under the normal operating condition. The next significance is the dynamic braking. Braking mechanism. When the supply voltage is removed, the motor is continued to rotate due to inertia, generating back EMF. If armature is connected to the resistor or short-circuited, the back EMF creates a current that generates a braking torque, helps to slow down and stop the motor. So the back EMF can be used as a braking mechanism in the case of motor as well. The next point is the feedback for control loop. The closed loop control. The closed loop control can be utilized this back EMF, such as in advanced motor control system, the back EMF can be used as a feedback to precisely control of the motor speed and position. By monitoring the back EMF, the control system can be adjusted the applied voltage to achieve the desired performance. So at the end we can say the back EMF is essential for efficient and safe operation of DC motors. It regulates the motor speeds, limits the starting and running current, and ensuring the energy efficient operation, and provide a natural braking mechanism and serve as a feedback control in the closed loop operation. And without back EMF, motor will be difficult to control and prone to damage and less efficient as well. Okay, now we will see how we can derive the torque equation for DC motor. See, torque is one of the important parameter for the DC motor. Okay, so torque is basically a rotational force produced by the machine when the machine armature is interact with magnetic field. It is a key parameter in both DC motor and generator, determining the machine's ability to perform mechanical work. Okay, let us start the derivation of torque equation for DC motor. See, the motor is rotating at the speed of capital N RPM, then the omega is the angular speed at in radian per second, which is equal to 2 pi n upon 60. As we know, n is the speed in RPM. So work done in one revolution is represented by capital W is equal to capital F into distance travel in one revolution, where work is defined by capital W and F is the force. So F into 2 pi R joules. Okay. So therefore capital P, which is equal to power developed, is equal to power done divided by time, which can be represented by capital F into 2 pi R divided by time for one revolution, which is equal to F into 2 pi R whole divided by 60 upon N. So at the end, how we can write this? F into R into 2 pi N upon 60. Okay. So now there is a relation between power and torque. So power is equal to torque into omega watts. Okay, where T is the torque in Newton meter and omega is the angular speed in radian per second, as I already mentioned. Let us assume that TA be the gross torque developed by the armature of the machine. It is also called armature torque, and gross mechanical power developed in the armature is EB into IA, where EB is the back EMF and IA is the armature current, as seen from the power equation. So if speed of the motor is n RPM, then power in the armature is equal to armature torque into omega, which means EB into IA is equal to TA into 2 pi n upon 60A. If you substitute the value of EB, which we have derived which we have derived in the previous slide, that EB is equal to P phi n Z upon 60A, that is the back EMF. If you put this particular formula in the in the place of EB, what you will get? P phi n Z upon 60A into IA is equal to TA into 2 pi n upon 60. So finally what you will get? Gross torque you will get is equal to 0.159 into phi into IA into P into Z upon A Newton meter. So this is the torque expression for the DC motor. Okay. For the better understanding of EMF equation and torque equation, let us solve some numerical problems. So let us discuss the numerical problem number 1, which is based on the EMF equation. Okay. So this numerical problem 1 states that the armature of a 4-pole 600 RPM lap wound generator has 100 slots. If each coil has 4 turns, calculate the flux per pole required to generate an EMF of 300 volt. So dear learners, first we need to understand what are the different values are given in this particular question. So total number of pole is given, which is 4. The speed of the machine is given, which is 600 RPM, and number of slots is given as 100, and each coil has 4 turns. Okay. If you want to calculate the total number of conductor is equal to 100 into 4 into 2, which is equal to 800. Lap wound generator, it is a lap wound generator, so L is equal to P, which means number of parallel path will be 4. So substitute those value in the EMF equation of a DC machine, which is EG is equal to P phi nz upon 60A. Substitute all those values, then by reshuffling what you will get the flux per pole is equal to, by substituting those value what you will get a flux per pole is equal to EG into 60A upon P into Z into N. If you substitute those values, then at the end what you will get the flux per pole, which is 37.5 milliweber. It is the value of flux per pole. So in this particular question, all the values are given except the flux per pole. Okay. So by substituting the values, we have find out the value of flux per pole. Okay. Now we will see the numerical problem number 2, okay, which is also based on the torque equation. Okay. So let us understand the numerical problem number 2, because the first problem is pretty easy, but this problem is a bit higher, a bit difficult, we can say. Okay. So a 4-pole DC motor takes an armature current of 6 ampere. The armature has 480 lap connected conductors. The flux per pole is 20 milliweber. Calculate the gross torque developed by the motor. So in this particular numerical problem, we have to find out the torque of the motor. Okay. So let us see what are the values are given in the question. So in this particular numerical, the flux per pole, which is the flux per pole P is equal to 4 is given. Okay. Armature current is given, which is 6 ampere. Total number of conductor, which is 480 is given, and flux per pole is also given, which is 20 milliweber. Okay. And one thing is also given, that is the lap winding is given. So in the case of lap winding, the number of parallel path A is equal to P. So as we have derived the gross torque is equal to as we have derived the gross torque, TA is equal to 0.59 into phi into Ia into PZ upon A. So here all the values are given. Okay. So by substituting the value of phi Ia, PZ and A, you will get the value of total gross torque. So by substituting, finally what you will get? You will get the value of torque, which is 9.159 Newton meter. Okay. So it is another problem. So now we will see the third numerical problem, which is also based on the EMF equation, which is also based on the utilization of back EMF. Okay. And here we have to calculate the armature current. Let us see the statement of the question. Okay. So a 220 volt DC shunt motor has an armature resistance of 0.5 ohm and field resistance of 110 ohm. If the motor draws a current of 10 ampere, then calculate the armature current. So here total current drawn from source is given. The total voltage applied across the DC shunt motor is given, and resistance of the field winding and armature winding is given. So please remember, let us remember the arrangement of a DC shunt motor. So in the DC shunt motor, armature winding is connected in parallel with the shunt field winding. Okay. So in that case, the line current is equal to armature current plus field current. If you substitute the values of IF and IA, then you will get the value of total line current. So in this case, line current is given. We don't know the field current and we don't know the armature current. So the field current can be obtained by using the formula IF is equal to V upon RF, where V is the applied voltage and RF is the field resistance. So by substituting those values in the IF formula, you will get the IF is equal to 2 ampere. Okay. Now the line current to be find the armature current. So the value of IL is given and IF we have find out right now. Just now we have found out the IF value. Now we will get the value of IA. So IA will be 10 minus 2, whereas 10 is the total line current and 2 is the shunt field current. Okay, IF value. Okay. So finally what you will get? You will get the armature value 8 ampere. So 8 ampere is the current which is flowing through the armature. So in this way you can solve the problem. In the previous problems, the questions are very simple, because single stage, you will solve the problems in a single stage. But in this particular problem, we have solved the question in 2 different stages. In the first stage, we have found out the field current, and the subsequent what we call the stage, we have found out the armature current. Okay. So let us see one problem which utilizes the formula of power as well, because in the statement itself power is given. So let us see the statement first. A 20 kilowatt 200 volt shunt generator has an armature resistance of 0.05 ohm and a shunt field resistance of 200 ohm. Then calculate the power developed in the armature when it is delivering the rated output. Okay. So first we have to visualize the arrangement of a DC shunt generator. Okay. So in the DC shunt generator, there is an armature, there is a field, and there is a shunt field winding, and there is a load. All three are connected in parallel. Okay. So in the case of DC shunt generator, the armature current is equal to the shunt field current and load current. That means IA is equal to ISH plus IL. Okay. And the terminal voltage is 200 volt. Okay. So all three elements are connected in parallel. That means this 200 volt is applied across the armature, it is applied across the field, and it is applied across the load as well. Okay. So what is the formula for power? So power is equal to terminal voltage into the load current. So P is equal to VT into IL. So the value of P is already given in the statement itself. It is 20 kilowatt. Okay. So substitute the value of P, and VT is also given, that is 200 volt. So substitute the value of P and VT, and you will get the load current, which is IL is equal to 100 ampere. So here what we have obtained? We have obtained the value of load current. Now let us find out the value of shunt field current. So as we know, the shunt field current is equal to VT upon RSH. VT is given, RSH is given. So ISH value is VT upon RSH, and the value of VT is 200 and RSH is 200, which means the ISH will be 1 ampere. Now substitute the value of ISH and IL in order to get the value of armature current. So armature current is ISH plus IL, which means 100 plus 1 ampere, which is equal to 101 ampere for armature current. Now by using those values, easily we will find out the induced EMF, which is equal to E is equal to VT plus IA into RA. Okay. So we know the value of VT, which is 200, plus IA, which is 101, and we know the value of what we call the armature resistance, which is 0.05. Substituting those value in the equation, what you will get the induced EMF is 202.05. So here as we know, the induced EMF is always greater than the terminal voltage, because there is some voltage drop in the armature. Okay, in the case of generator, and in the case of motor, applied voltage is greater than the back EMF, because some voltage is drop in the armature. Okay. So now let us find out the value of power developed in the armature. So PA is equal to E into IA. Okay. So E we have derived, that is 205.05 into 101, which means what you will get? You will get the total power developed is equal to 20.71005 kilowatt. So it is the power developed in the armature. Let us see some more numerical based on this EMF equation, and based on this EMF equation, torque equation, and power of the DC machine. So let us see the next problem. The armature of 6-pole DC generator has a wave winding containing the 664 conductors. Calculate the EMF generated when the flux per pole is 0.06 Weber and the speed of the machine is 250 RPM. At what speed must the armature be driven to generate an EMF of 250 volt if flux per pole is reduced to the 0.058 Weber. So in this equation, earlier the motor condition, in this particular question, earlier the generator parameters are different, and we have to calculate the calculate the speed at some different condition. So let us see what are the values are given. So in this particular question, number of poles are given, which is P is equal to 6, and here there is a wave winding, which means number of parallel path is equal to 2, and total number of conductor is equal to 664, and flux is equal to 0.06 Weber, and the speed in the condition 1 is 250 rpm. So with this particular set of with this set of specification, let us find out the EMF, induced EMF in the machine. So let us put the value of phi, P, Z, N1 and A. So ultimately what you will get? You will get this induced EMF is 490 volt. So it is the EMF generated in condition 1. Now in the condition 2, the flux per pole is changed, and subsequently the EMF, induced EMF is also changed. So now earlier the flux per pole is 0.06 Weber. Now now it is reduced to 0.058 Weber, and induced EMF is 250 volt. By substituting those values in the EMF equation, what you will get? You will get the second speed. Okay, so substitute those values in the equation, then you will get the value of N2 which is equal to 129.83 rpm, which is closely equal to 130 rpm. So in this way you can solve the problem, whereas two different flux per pole are given. Okay, earlier the flux per pole is higher, and in the second condition it got reduced. So in this way you can solve such kind of numerical problem. Now we will see one more numerical problem, which is based on the compound generator. Okay, so which says that a short shunt compound generator deliver a load current of 30 ampere at 250 volt and has armature, series field and shunt field resistance of 0.05 ohm, 0.03 ohm and 200 ohm respectively. Calculate the induced EMF and armature current. Allows 1 volt per brush for the contact drop. Okay, so it is a very nice problem. Let us see how we can solve this problem. So in this question, the load current is given. Let us imagine the typical circuit diagram of a short shunt compound generator. So as you can see in the figure, the short shunt generator is presented. Here the load current IL is equal to 30 ampere is given, and terminal voltage VT is given, which is 250 volt, and armature resistance is given, which is 0.05 ohm, and series field resistance is given 0.03 ohm, and shunt field is also given, which is 200 volt, and voltage drop across the brushes is also given, which is 1 volt per brushes. Okay, so in order to get the value of voltage across the armature, how we can find out? So AB is equal to VAB, which means AB is the what we call the voltage across the armature, which is equal to terminal voltage plus IL into RSE, whereas RSE is the series field resistance. So substituting the value of VT, IL and RSE, what you will get? You will get the voltage across the armature, which is 220.9 volt. Okay, so now substituting this value, so there are two ways to find out the voltage across the armature. The first method, by first method we have derived the voltage across the AB. Now we can derive the AB with the help of this voltage drop across the brushes and the induced EMF. So VAB is equal to E minus IA into RA minus V brushes. Okay, so substitute the value of VAB, which is equal to EA. We have to find out the value of EA minus IA is given, RA is given, and voltage across voltage drop across brushes is also given. So in this case there are two brushes, so minus 2. So here we have to find out the value of IA. IA is not known. So how we can find out the IA? IA can be find out once we have find out the value of ISH. So ISH will be VAB upon RSH. So VAB we have just now we have obtained, that is 220.9 volt, and the value of RSH is known, that is 200 ohm. So ISH is equal to 1.1 approximately. Okay, so substituting the value of ISH in the above equation, what you will get? You will get the value of IA. So IA is equal to ISH plus IL. So ISH is equal to 1.1 and the IL is equal to 30. So 1.1 plus 30, which means what you will get? You will get the value of IA, which is 31.1 ampere. By substituting the value of IA in the above equation, for finding the EA, what you will get? You will get the value of induced EMF. So induced EMF will be 224.45 volt. So this value will be induced in the armature of the DC shunt compound generator. Okay. So this induced EMF will be generated in the short shunt DC generator. Okay. So in this particular lecture, we have seen how we have derived the EMF equation for DC machine. Also, we have seen what are the different significance of back EMF in the DC machine, and we have derived the torque equation for DC motor. Also, we have seen how we can derive the torque equation for DC motor, and at the end we have seen the different numerical problems associated with this EMF equation, torque equation and power equations. Okay, and following references I have utilized for this particular lecture. You have to go through it. Thank you.